Welcome friends. In our previous number lecture, we have completed the 90 number question, and that question was about the beta decay transition rule. You know the Gamow-Taylor transition rule, the Fermi transition rule. Okay, so all was on that topic. But in the today's lecture, we will do the 91 number question, and this question was about the Bethe-Weizsäcker empirical mass formula. You see, Bethe-Weizsäcker empirical mass formula. And as you know, in nuclear physics, this Bethe-Weizsäcker formula, empirical mass formula, is also known as the semi-empirical mass formula. And this formula is linked with the stability of the nucleus in the form of a binding energy. Okay, so the formula we can write as this. You know, there are five terms involved in the Bethe-Weizsäcker empirical mass formula, that is the semi-empirical mass formula. The first one is for surface energy, the second one for the first one for volume energy, the second one for the surface energy, and the third one for the Coulomb energy, and the fourth one for the asymmetric energy, and the last one is for the pairing energy. Okay, so let's write one by one. EB, which is a function of, that means the energy, binding energy, is proportional to AZ is equal to AV, volume energy term, minus AS, surface energy, to the power A to the power 2 by 3, minus AC, Coulomb energy, Z into Z minus 1 divided by A to the power 1 by 3, minus ASY, A minus 2Z whole square divided by A plus or minus AP. This is the pairing energy, A to the power 3 by 4. Okay, and this pairing energy term is 0. Del P is 0. Pairing energy contribution is 0 for even or or you can say for odd even nucleus, and this nucleus is collectively known as odd A type nucleus. Okay, but the contribution for nucleus whose atomic number, or you can say the nuclear number, are even or odd has a contribution to the total binding energy. So in our question it is given that in the option number A, it is given that the asymmetric energy is proportional to this A minus 2Z square divided by A. You see, this is the asymmetry term. This is the asymmetry term, and this proportionality is correct. So option A. So option A is the correct one. Now let's see what is given in the option B, C, and D. Okay, you see in option B it is given that pairing energy is proportional to A to the power minus 3 by 2 for odd A type of nucleus. Now I have recently told you that for odd A type of nucleus, it is 0. The contribution for pairing energy is 0. Okay, for even odd or odd even type of nucleus, for odd A type of nucleus, the pairing energy contribution is 0. But here it is given that it is proportional to A to the power minus 3 by 2. So option B is incorrect. Now let's see option C. It is given that Coulomb energy is proportional to Z into A to the power 2 by 3. Now you see the Coulomb energy here is the Coulomb energy. is the Coulomb energy, and it is proportional to Z into Z minus 1. That means the EC Coulomb energy term is proportional to Z square. We can see, we can say like this, because there are two Z term here. But here in the option, it is given that it is proportional to only one Z here. Only one Z is present. So option C is also incorrect. Now let's see option D. It is given that surface energy is proportional to 8 to the power 1 by 3. Surface energy, let's see the surface energy. Here the surface energy. Okay, the surface energy is proportional to 8 to the power 2 by 3, not 1 by 3. Okay, so that's why option D is also incorrect. Okay.